Today I'll tell you about our paper, Random Order Set Cover is as easy as offline. This is joint work with Anupam Gupta from CMU, Greg Kehne from Harvard, and I'm Roie Levin, also from CMU. What's the set cover problem? You're given a collection U of n elements and a collection S of m subsets of those elements. And what you'd like to do is pick the smallest number of the subsets to cover all the elements. In a picture, perhaps the dots represent the elements and the ellipses represents the subsets. And you'd like to pick the smallest number of sets to cover the elements. So perhaps this collection of red shaded sets is a feasible solution. What is the online version of set cover? This is a classic problem introduced by Alon, Arbu, Hazar, Buchbinder, and Naor in 2003. And it's the same thing. We're solving set cover, only now we'll assume that an adversary chooses this collection of elements, and it's unknown to us initially. Instead, the adversary is going to reveal it to us one by one online. So initially we have these sets, which we don't know anything about. And then when an element arrives, that element tells us, hey, I'm part of the following sets. And when it arrives, we need to immediately pick some set to cover it. Okay, so perhaps this element V1 shows up and we pick this subset to cover it. An element V2 shows up and it tells us it's part of this set. So we pick this set to cover it. V3 shows up, it tells us which sets it's part of. It's already covered, so there's no need to do anything. And this game continues. And the goal is that at the end of this process, the total number of sets that we picked over the course of this game be not too much more than the offline optimal solution to the set cover instance that's given. So finally, what's the random order version of the problem? It's the same thing. We'll still imagine that an adversary selects a set of elements to show us online. Only now we constrain the adversary to roll some dice and shuffle the order of the arriving elements uniformly at random. Okay, so perhaps this is the set system that it picks, and this is the order that comes out of the dice roll. And now we play the online set cover game only with this uniformly random order. So the question that we answer in this work is this random order version of the problem more like the offline version or more like the online version? The adversary is weaker, but how much weaker? So maybe the title of the talk gives it away, but I'll pretend that you are in suspense. So what's known? Well, for the offline version of set cover, a classic approximation algorithm's result is that there is a log n plus 1 approximation algorithm for that problem. For example, the greedy algorithm achieves that guarantee. In the original paper, Alon et al., as well as a long line of follow-up work, show that even though you have incomplete information, you can still be competitive, but you lose an extra log. So they show that you can get a log n times log m competitive algorithm, where n is the number of elements and m is the number of subsets. I'll mention one more related result, which I'm calling the stochastic version of this problem. So in a 2008 paper, Anupam and a group of co-authors show that if you assume that you're playing online set cover, but you assume that the elements are being drawn IID from a known distribution, then you can avoid the double log, and instead you can get log m times the support size of that distribution. All right, so what can you do in random order? Well, there's some reason to believe that you can't beat this log n times log m, and we'll talk about those reasons in the future. But actually what we show is that for an even more general problem, which I'm calling random order covering IPs, you can actually beat the double log, and you can get a log mn, where m and n are inside the single log. So at least in the regime where m is polynomial in n, this is matching up to a constant, the best possible offline bound. We can think of this as an improvement over the stochastic version in two senses. So one is that we're making the support size term n is the number of elements that we actually see, as opposed to the universe of elements that we could see. And the second thing is that there they assume that you know the distribution, and random order is essentially equivalent to the unknown distribution version of the stochastic setting. Now, I'm not giving that paper enough credit. It has some additional interesting properties, but at least under this benchmark, this is kind of a strict improvement. So our paper is not just a new analysis of an old algorithm, it is actually a new algorithm. And in some sense, what we're showing is that it's possible to learn the distribution, the unknown distribution over the elements, and to solve the set cover instance without taking too much of a hit at the same time. Let me just briefly mention what the covering IP problem is. So here's the problem. An adversary is going to choose a covering IP instance, and the constraints are unknown to you initially, the adversary rolls some dice and then shows you these constraints to the covering IP in random order. And the goal is to maintain a feasible solution X to this IP, excuse me. And the hard part is that this solution X must be monotonically increasing. So you're never allowed to decrease a coordinate once you've increased it. And you'd like the total cost at the end of the algorithm to be, competitive with the offline optimal solution to this IP. So Satcover is nothing but the special case of this where the constraint matrix is 0, 1. So really we solve this fully general problem. Okay, in the remainder of the talk, I'll briefly sketch the previous work. So the algorithm for the adversarial order case, that's probably where you'd start to look if you were trying to solve this problem. We'll talk about why it doesn't work. And then I'll tell you about our algorithm, which we call learn or cover. I'll more or less do a warm-up exponential time version in full detail, and I will sketch briefly how you can make it polynomial time, and then spend a short amount of time talking about extensions and lower bounds in our paper. Okay, so how does this Lund paper work? It's a two-stage algorithm, which at this point has become a fundamental primitive in online algorithms. So step 1 is you solve an LP relaxation of Satcover online, and step 2 is you round this relaxation online. So here is the classic Satcover LP. We have a variable XS for every set. We'd like to minimize the total number of sets chosen fractionally. And we have a constraint for every element V that we need to cover, that at least one set be picked fractionally containing this element. And everything must be non-negative. So the meat of their paper is to show that what you can do, even as these constraints for every V are arriving online, you can maintain a solution X that is only monotonically increasing, so no coordinate of this vector X ever goes down. And furthermore, this X is log M competitive with the final solution. Okay, so these two guarantees are at tension with each other, and this is the interesting part of their work. And this guarantee is somewhat magical because it allows you to round online in the following sense. So if this is your vector X at time t, and this is your vector X at time t plus 1, so because of the monotonicity property, the delta is only ever positive. What you can do is you can take each, by each coordinate S with probability that's only proportional to the change delta XS. And you can do this in such a way such that the probability that you take a set S at the end of the algorithm over the course of the entire algorithm, not just at a single time step, is exactly the final LP value XS. And so it suffices to analyze independent random rounding as if it were performed one single time offline. Okay, so the way you usually analyze this is you say, well, every element is covered with constant probability if I take every set with probability XS. If I repeat this log n times, I boost the probability to 1 over n or 1 over poly n, and then you can union bound over the elements, and this is how the analysis goes. So the expected cost of this algorithm is order log n times log m. Log m comes from the fact that we're only maintaining a log m approximate solution to the LP, and log n because we're performing independent random rounding. So it turns out that neither stage of this Lund algorithm can be improved in random order. So there are situations in which independent random rounding necessarily loses a log n. So that part is tight. And we show that actually log m is a lower bound even for fractional algorithms, even in random order. And so you can't hope to kind of independently improve either stage of the analysis. And actually, nor can you improve them together. So there's situations in which the Lund algorithm does actually get omega of log m times log n, even in random order. So that algorithm will not beat this double log bound. A new algorithm is indeed needed. And the way that we circumvent these seemingly damning barriers is that we maintain, you can think of the algorithm as maintaining a coarse solution X, which is neither truly feasible nor truly monotone, and yet can be rounded online in random order in such a way that it satisfies the claimed guarantees. Now, if that sounds mysterious, hopefully it'll be more clear kind of in the remainder of the talk. Okay, so let's jump into our algorithm, and it's called learn or cover. This is the exponential time variant, and we're only going to talk about the unit cost setting. Okay, so to understand this algorithm, we'll imagine that there's two objects floating around of interest. One is U, the set of unseen elements that are going to arrive that we don't know. And the second thing is this thing I'll call P, or the portfolio. So let K be the size of the optimal solution. You can assume using standard tricks that you know this value K. We'll think of P as the collection of all possible solutions that could be the optimal solution. So initially, when we start the game, we haven't seen any elements yet. We have no information at all. So we should initialize P to be all possible K tuples of the set S, which is the collection script S of subsets that we're allowed to pick. Okay, so P is initially all K tuples of subsets. Now here is the algorithm. At time t, the element V arrives. If V is already covered on arrival, there's no need to do anything, right? That's like the example we saw at the beginning of the talk. On the other hand, if V is uncovered, we'll do two things. We'll pick a T uniformly at random from our portfolio P, and we'll buy a random R from T. So recall the type of P is the set of all K tuples. So T that we sample is a K tuple of sets. And so we can pick a random set from this K tuple R. The second thing we'll do is that we'll prune our portfolio after we've sampled. So any tuple in this enumeration of all possible K tuples that doesn't contain the element V that arrived, we remove from the portfolio. Okay, now you might complain, all we've done is sampled some R from a kind of wacky distribution and then pruned our portfolio. Why should we have covered the incoming element V? And indeed, there's no guarantee that we will. So we'll do one more thing, which I'll call the backup step. We'll buy an arbitrary set to cover V. Great, that's the entire algorithm. How do we analyze it? Well, in rounds in which V arrives covered, no need to do anything. The algorithm pays 0, right? So it suffices to count the number of times that the algorithm lands in this else clause, right? And when we land in the else clause, you pay 2. You pay 1 for R, and then 1 for the backup set to cover V. So if we can bound the number of times we land in this else clause, we'll be done. Here's how we do it. There's two cases. In case 1, at least half of the T and P cover at least half of the remaining uncovered part of U. Okay, so we should think of this as most of my portfolio is pretty decent. Half of the T cover at least half of U. Okay, so I claim that if this is the case, then the R that we sample covers at least 1/4K of U in expectation. Why is this? Well, half of T cover at least half of U, so the T that we pick should cover like 1/4 of U. And then we pick 1 of K of the sets in T uniformly random, so that's like 1/K of what T covers, so 1/4K. Which means that if we're in this case 1, then U should shrink by 1 minus 1/4K in expectation. We'll imagine that we also prune U of anything that we covered. Okay, case 2 is at least half of T cover less than half of U. I should think of this as most of my portfolio is pretty bad. Well, in this case, then what I claim is that condition on landing in this else clause, what we're doing is sampling uniformly at random from the uncovered part of U. Okay, and I know that most of my sets T don't cover most of U, which means that there's a good chance that this incoming element will land like outside of a lot of the T's, right? So in fact, half of the T's in my portfolio will be pruned with probability 1/2, which means that P should shrink by something like 3/4 in expectation, right? I'll toss like 1/4 of the tuples out. Now we're almost done. Oh, sorry. So the picture we should have in our heads is that we're running this algorithm, and we're slowly taking bytes out of either U or P. Okay, in case 1, we take a byte out of U. In case 2, we take a byte out of P. And now we don't know necessarily which case we're in, right? Like we don't know U, and we can't evaluate which case we're in, but either way, we're sort of taking bytes out of one or the other and marching along. So just to wrap up the analysis, so I said that in case 1, which I'm suggestively calling a cover step, U shrinks by 1 minus 1/4K in expectation. In case 2, which I'm suggestively calling a learn step, P shrinks by 3/4 in expectation. And we're either in one case or the other. So U is initially N. The size of U is initially N. So how many cover steps suffice until we're done? Something like K log N, right? On the other hand, P is initially M choose K. The size of P is initially M choose K, something like M to the K. How many learn steps suffice until this goes down to 0 or to less than 1? Also K log M, right? And I claim that, if either the size of U goes down to 0, then we've covered everything. If the size of P goes down to 0, then or down to 1, whatever, we've identified the optimal solution, we're also done. So if either of these hits, goes below 1, we're finished. And so it means that after K log N plus K log M steps, we must have done either K log N of cover steps or K log M learn steps, which means that K log Mn steps suffice until this process terminates. That's basically it. The kind of remainder of the paper and of the talk is dealing with the interesting question of how to make this poly time. Okay, so this is clearly exponential time because one needs to enumerate all possible solutions initially. But we'd like to reuse the intuition that an algorithm can either make progress learning about the optimal solution or covering. And indeed, this is what we do. So the polynomial load time version of our algorithm, at least the unit cost version, what it's doing is something very similar. So instead of enumerating all possible solutions, what it does is it just directly maintains a distribution, okay, which I'm calling X. And X is initially, so it's a distribution over sets. You have no information initially about the set system, so it makes sense to initialize this distribution to the uniform distribution over the sets at your disposal. And now we do something very similar to what we did in the exponential time version. When an element V arrives at time t, if V is covered, do nothing. Otherwise, first buy a random set R from this distribution, and then update the distribution in some sense. Okay, so here's how you update it. For so an element V arrives, you'll give a small boost to all the sets containing V. So for all S containing V, just multiply the probability of that set by a constant, say E, and now renormalize to make sure it's still a distribution. And again, we do this backup step. So the kind of like right analog of the way that we analyze the exponential time version is to measure convergence of this thing with a potential function. And here is the potential function. Basically, it's like some weighted combination of the KL divergence between the optimal solution, X star, and XT. And we're imagining that X star is really scaled down so that it's a distribution. Okay, it's like 1 over K on the support of opt. And XT is the solution that our algorithm is maintaining at time t. Plus, the second term in this potential is log of the size of UT, where UT is the uncovered elements at time t. Okay, so just to remind you, like this is the kind of formal definition of the KL divergence. And the proof proceeds with the following set of claims. So first you show that phi 0, the initial potential is not too big. It's something like log mn. It never goes below 0. And the second claim is that in rounds in which we land in this else clause, okay, when VT is uncovered, again, we pay 2, we buy a random R and we buy the random backup set. Well, this potential decreases by something like 1 over K in expectation, okay? And I claim that this suffices because, if the potential starts at log mn, after K log mn steps, in expectation will go down to 0. In each one of those steps, we pay 2, so that's a total cost of something like K log mn. Okay, so the key to the proof is to bound the expected decrease of the blue part and the expected decrease of the red part separately. The blue part only depends on the choice of the random set R. And on the other hand, the red part only depends on the random element that's incoming V. And so one can kind of cleanly do these two analyses separately. And the decrease in the red part is where we indeed use the random order assumption. Okay, so I don't have time to do this full proof. What I'll do is I'll just like flash it, and you can pause the video and kind of go through it in detail if you'd like to. But essentially, like these two claims that I talked about are what we show. you bound, so if VT arrives uncovered, you can bound the decrease in the red part of the potential over the randomness of the arriving element V. And on the other hand, if VT is uncovered, you can bound the decrease in the blue part over the randomness in the set R that you pick uniformly at random. And I mean to show you this just because it's a relatively short and clean algebraic proof. But the point is that, okay, you can bound the decrease of the red part like this, you can bound the decrease over the blue part like this. And notice that the positive term in the red decrease looks a lot like the negative part of the blue decrease. And so when you sum a weighted combination of these two terms, what you get is that they cancel out cleanly, and the decrease in the potential is exactly the negative part of the red portion, so -1 over k, which is what we wanted to show. Okay, and since as I said, since phi 0 is order log mn, the expected total cost here is k log mn. All right, that's basically it. So let me just mention a few extensions and lower bounds. So as I said in the start of the talk, so we really show this for a much more general problem. So for pure covering IPs in random order with general costs. And we show a few interesting lower bounds. So you can wonder like how much the random order is truly necessary. And what we show is that, well, for a batch version of the online set cover problem, like random order online set cover, where in every round, instead of getting a single element, we get a batch of elements, where the batches are adversarially chosen, but the order of the batches is uniform random. You can't hope to beat this double log. Okay, so this version is truly harder. And as a corollary, you can show that extensions of online set cover, for example, like online submodular cover, also need to suffer a double log in random order. And I haven't defined these parameters, but come find me and I'll tell you more about this problem. I'll just say to end that it's a nice open question if this bound can be matched. So an almost matching upper bound was shown in a previous work of mine with Anupam, but the question is if you can remove kind of an extra end inside one of the logs. So with that, I will conclude. Thanks so much for listening to the talk, and please reach out with any questions you may have.